Okay, students, welcome to the first year of the elective when structure is architecture. It'll be being co-taught between myself and Dave Bowick. Unfortunately, we probably won't be filming them simultaneously. We have made the decision to, our 4-year-old is supposed to be starting school this year. And it just seems a lot to send a little kid to school in these circumstances. And we're in a town where most people aren't. And if he went to school, he wouldn't be able to play with any of his friends. So we made a hard choice to do that. But it means we will be having once we have the 4-year-old home and we have someone helping out at home 2 days a week, we keep the 2-year-old home as well. So we're going to be very, very busy, but we also have all of you lovely students. I will also be teaching the structures curriculum for both the undergrad and the graduate program this fall as well. So I have lots of students on my plate, and I want to be available for everyone, and we don't even have a TA for this course. And I know that there was a lot of you on a wait list, and I said, you know what, we'd take up to double the students, and it looks like the administration definitely took me up on that. So we have double the normal elective allowable students in a course. So we're all going to have to be really patient with each other. So when structure is architecture, so we're going to be working on exploring the science behind architectural elements that expose their structural form. So these are the things that are very much governed by architecture. They are usually highly thought about. They're often feature items on a project. Not always. Sometimes they're purely about function. But they're usually given a lot of love and care by the architect or landscape architect. Because of that, or because of the type of forms they are, often the structure makes up a large portion of what you can see. So in those cases, the architect and the engineer really have to understand each other's limitations. So the engineer has to understand what's driving the decisions for the architect, and the architect really needs a good grasp over what the engineer is doing and why they're doing it, and what are the key spots, what are the places you can't mess with, and what are the places you can. So we're going to be talking about what parts of structure govern these things, and we'll even, it's not our job to know part 3 of the building code very well, but both of us have done these things enough that we have a pretty good grasp over what the architectural requirements are, and usually what's kind of driving the kind of ethos of these things, and that can change, but it's worth letting your engineer know when you're trying to do something different from the norm. Long before COVID hit, when I agreed to teach 3 courses this term, we also agreed to start writing a textbook with the Canadian Wood Council on designing with wood. So I'm writing the structural engineering component, which is just teaching architects basic structural engineering, which, as you can imagine, is very similar to Structures 1, what we did, and some of Structures 2. I'm assuming most of you were actually my students at some point. There's probably a few of you that aren't. Anyway, we made that commitment long before COVID hit, and now we're in the thick of our commitment. The deadline's coming up, and we're obviously in a panic. So when we hired someone to help look after the kids, we said, will you look after them for the whole week so we can go somewhere and write quietly? And luckily we have a cottage north of Kingston, so that's where we are this week, and where I'm filming this week's lecture. It is a very small cottage. We're stepping over each other's toes. Dave's on a conference call right now, so he's sitting on the porch in the cold. But we do have, if it'll focus, this beautiful view. So I apologize that the light will be going in and out, but at least when it's not focused on me, you're getting that beautiful view to hopefully make you want to listen just a little bit more. So let's start talking about what we're going to do in this course. This is going to be a very short, light lecture. It's more just to kind of introduce you to the concepts. It's an elective. There will be a little bit of pen to paper, but not very much. It's mostly what we want is when you go out in the world and you're designing these elements, that you understand where they're coming from. It's really tough. I always take the philosophy, and I know Dave does as well, that it's not our job to say no to architects. Some engineers don't feel that way. Hopefully it's not the majority of them, but I know engineers really like to be right. So hopefully when you're now designing these things, when you go to an engineer with your concept on paper, you'll already have something that's in the realm of working. It's really tough when some of these beautiful conceptual things, and they're not possible. They can't work without a lot of compromise. And we want to make sure you don't have to make that compromise. You understand what these driving factors are before you even start your design. So, like I said, probably the majority of you have been in my class before. So you understand the way my lectures work. Slightly different format because we're doing this online. But I think even some of you were in my class last term when we had to do 2 or 3 lectures online. I think this is a better format rather than me standing in front of my living room filming the lecture. It's slightly less anime. I'm used to walking around while I teach and kind of getting pretty involved in my lecture. It feels a little weird just to sit here, but we're going to make it work. There will be a PowerPoint that I'll upload every week to Quercus. I'll then upload this video on a page in the module that gives you the link to YouTube for it, which obviously you've already found if you're watching this video. The first slide of each lecture module, or each module, because we might in a particular lecture have 2 or 3 videos that are, if we have smaller components, we might break it up into smaller components. Because I think there's one week where we do playground structures and lampposts and something else small. All things that they have the same, usually the same kind of driving factors in what kind of governs their design. And so those might be lumped together, but with 3 separate videos that we'll go through. My goal is to have the PowerPoint presentations and the videos up online for you on Wednesdays. I'm going to try to be pretty rigorous about that just for my own sanity. Like I said, I have a 2-year-old and a 4-year-old at home full time. We have help from 9 to 5 on Tuesday, Wednesday, Thursday, but that's it. And they're in the house still with us. So you may see little munchkins run through periodically, and hopefully I don't have to deal with any major calamities with them. Well, if you see me run away and stop the video abruptly, it's because some sort of fight has broken out. They don't fight very often. They're pretty good that way. So if you do email me with a question, feel free to use Quercus or email. Just let me know what class it is, simply because they all touch on sometimes similar topics, just loosely, or you know, that assignment or this question or that slide 10. I need to know what lecture we're talking about, because it's not always intuitive just by reading the question. If you have questions, we'll answer them. If it's a really good question or a question that we think lots of people are dealing with, if we don't answer you, it's because we're taking that question and we're going to add it into the next week's video, or we're going to make a mini video addressing that question specifically. So if you have a great question or one that we think everyone is confused on, we can at least make sure the entire class gets the benefit of that information. So today's lecture is mostly just a structural refresher, just to remind yourself of the nomenclature and what we're going to look at the beginning of each lecture that kind of lays the groundwork for how we're going to proceed with that. So I'm just quickly going to go through the types of loads. We're going to just refresh ourselves on vectors, because one of the things, as much as we're going to do very little math, drawing free body diagrams is going to be a big part of this course, because that is literally what an engineer does when it's time to solve a problem. In Structures 1 and Structures 2, it didn't appear that we drew a lot of free body diagrams, but every time we drew a beam loading diagram, we were drawing a free body diagram. So we're going to go through that, and they're going to be more unique and sometimes more complex, but also sometimes even more simple. And you're really going to kind of grasp that idea of strength, stiffness, and stability. The free body diagram really helps us make sure that we have a stable system. Do we have a way to resist all of these loads acting on it? We're going to remind ourselves about limit state design. We're going to talk about the types of loads, which is on there twice, but I'm talking about two different things when I say that. And then just a quick brush up on steel, wood, and concrete, which are the three main materials. We will talk about a few other material choices, especially where a lot of these things are kind of small scale, high-end installations. We'll brush on aluminum a little bit. We have a whole lecture just about glass, so talking about the limitations of glass. And sometimes other materials come into play. But steel for a lot of these, with touches of wood and concrete, and then probably aluminum are going to be the majority of the things we talk about. And we'll bring up aluminum when it comes time to talk about aluminum for those particular objects. And then we're going to talk a little bit about what we're going to think about at the beginning of each lecture module. So if we're talking about canopies, what loads would we use for that? What serviceability criteria would we use? Do we need to do a vibration check? And so I'll remind us on what all of those things are, and then at the beginning of each module, we'll actually talk about those things and how they apply to that particular thing we're going to look at designing that day. So statics, which is what we want everything to be. Statics is basically the art of staying still. We do not want our things to move. So statics is the branch of mechanics that is concerned with the analysis of loads, so that could be force or torque or moment, on a physical system, so our object, in static equilibrium. So we don't want it to move, and we want to know what all those forces that are applied are doing internally to our object. So that is in a state where the relative position of subsystems do not vary over time, or where components and structures are at a constant velocity. So again, it's staying still and it's not rotating. So equilibrium is when it's not moving or rotating. In our study of statics, if it's moving, it is not in equilibrium and we are unhappy. We have failed in what we're trying to do. That said, sometimes there are things within the subsystem that move. Sorry, I'm coming in and out of focus there. And obviously deflection is movement, but we're talking about the object system. So the object system isn't sliding, 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 spinning, spinning, spinning. So in any particular thing, we have 6 degrees of movement that can possibly happen, and we want to make sure none of them are moving. So everything is subject to loads in the world. Right here, while I'm sitting here, I'm subjected to gravity. I'm trying to sink down into the center of the earth. The fan is blowing behind me, not very strong, but the fan is blowing behind me, trying to push me over. If I had a bowl in my hand of soup, it's adding weight to my body, and I need something to be able to resist that load. My own body has weight to it. We want the structure not to move or remain in equilibrium, so there needs to be an equal and opposite force that's keeping me in place, or a reaction. So we need to know that every system we talk about in this course, for every load that is applied to it, has a reaction. So its own self-weight, trying to push it down into the ground, we need something to push up to resist it. If its own self-weight is trying to cause it to tip over, we need some sort of couple or moment reaction to keep that from happening. So everything is going to need to have a reaction to stop this movement or to keep the system in equilibrium. So with all of that, we're going to need forces, and we're going to need to be able to talk about the forces that are applied and the forces that resist the load or the reactions. Don't worry about this too much. This is just kind of a reminder of what a force is. So Newton's second law is that force is the product of mass and acceleration. Well, mass is the same no matter where you are. Doesn't matter what planet, doesn't matter what gravity is. Acceleration is how much you try to move into the center of the Earth of that particular object. So our acceleration on the moon is different than our acceleration on Earth. That is where weight comes in. So on both the moon and Earth, your mass is the exact same, but your weight might be different because it is your mass times your acceleration. All those imperial nuts with pounds can be used for both mass and weight interchangeably. They add units to it, but then they often make it disappear because often you're on Earth and you ignore that part of it. We have a very kind of distinct way of distinguishing that. We often colloquially refer to mass and weight as the same thing, but weight is when we actually are talking about our force that we're trying to push down into the Earth with. So because of that, in metric, we're often talking about kilograms as our mass and newtons as our weight. So how much we're trying to go down into the center of the Earth. 1 Newton is kind of hard to get your head around, but it is 1 kilogram trying to move 1 meter into the center of the Earth at seconds squared. Almost irrelevant. The best way to think about it is 1,000 newtons or 1 kilonewton is about 225 pounds. And I think I show that in this slide in a minute. So 1 kilonewton is about 225 pounds. Maybe I'll add that slide in for you guys and repost that. Let me. Dave took my pen. So I'll add in a slide to remind us. Maybe I can find another pen here. I'll be right back. I'm just going to find a pen so I can remind myself to write that into the slideshow for you guys. Okay, I'm gonna put a refresher of the units. I'm gonna add the units so you guys have it. We're not gonna spend a lot of time talking about that stuff, but sometimes we might kind of just quickly refer to something, and it'd be nice for you guys to just have a handy list of what those kind of normal units are and kind of the interchanging we do back and forth. So moment is another type of force, and it's what causes a body to rotate or spin. If you apply a force or a vector or a load eccentric from a body's center of mass, it will cause it to rotate. The farther the force is away from the center of the object, the more it wants to rotate. You understand this concept when you're talking about levers. The longer the lever, the easier it is to make the thing lift up. It's because you are applying more moment to it with the same amount of downward force. You've moved that force further away, which causes more moment on the system, which makes it easier to lift that object up. So intuitively, you have this understanding of moment and how to make it work better. For those that took my course in the past, know that I often demonstrate this with a teeter-totter. 2 people, the same weight, sitting the same distance apart on a teeter-totter are going to balance each other out. Move one of those people just a little bit, and you're going to have a system that moves. So not in equilibrium anymore, but having rotation or moment on the system. So moment is really just a descriptor of that force and its distance. And the way we talk about it is the force times the distance. So the further the thing is away from the centroid, the more moment on it. We talk about our force in kilonewtons or newtons quite often, and we talk about distance in meters when we're talking in metric. So often we'll be referring to our moment in kilonewton meters. Sometimes when we're talking about strain and stress, we might change that to Newton millimeters because we need to work through some equations, which we're not going to do that much of, but you might see us switch between kilonewton meters and Newton millimeters periodically. So this object here, you can see we have a force right here, and we're some distance apart from our centroid. So you could rewrite this system as a moment causing it to spin, where the moment is force times eccentricity. but we still have this force right here acting on it. So this object is going to try to spin and slide. And you can see here, this force would have caused this to spin and slide simultaneously. Equivalent force couples is when we use two forces to ensure the object doesn't slide, but might still cause a moment, or resist an applied moment if we had an applied moment and we were trying to talk about how we could resist that load. So you can see here we have two forces, each some distance away from the centroid. So our moment here in the equivalent system has m equaling force times eccentricity plus force times eccentricity. But look, this force is trying to push the object in that direction, and this force is trying to push the object in that direction, so they're going to balance each other out. So we have it in equilibrium from going up and down, but the object's still trying to spin. If we had some other applied moment that we were trying to resist, this might be a good way to resist that moment if we needed to. Free body diagrams. Free body diagrams are a really handy tool to take a complex system and distill it down to a very simplistic drawing to make sure we understand what all the loads are on it and how we're resisting these loads. Even still, sometimes senior engineers they can't solve a problem. They take the second to draw the free body diagram, and it kind of crystallizes the idea, oh, I need a reaction here, so I need to put something there that can resist the load there. And so we do that often by drawing a simple stick figure and representing all the forces and moments as vectors. So for every free body diagram, we need to draw all the forces and all the moments and all of the reactions on the system. Once we've done all that, we've kind of drawn a free body diagram. For statics, which is what we're studying, the sum of all of these things in every direction and about every axis needs to be zero. That's what we want, to know this thing is in equilibrium. If we sum up all the forces that might be acting on the object up and down and any reactions we have on the object, the sum of all of those forces in the up and down direction need to be zero. The sum of all the forces in the side to side direction need to be zero. The sum of all of the forces in and out of the page need to be zero. Spinning about every reaction or every axis needs to also be zero. The sum of all of those moments needs to be zero. We often find that a little bit overwhelming, and quite often we'll break it down into a 2D world just because it's easier to get our head around it. Understanding that there's depth to the system, and sometimes what we'll often do is maybe solve the problem on all three planes if we need to, but often just breaking it down into a 2D plane solves all of the loads that we need to think about. We can often get away by doing it in a very simplistic 2D way. If it's a bigger system, sometimes it needs to be a bit more complex than that, but often drawing one kind of 2D plane free body diagram will often get us all the things we need to do. So every free body diagram should contain all the forces acting on the body. And if that's through the center of mass, we kind of need to show that in some way. All of the moments acting on the body, any restraints that are keeping the body in equilibrium, which are technically also forces. Our reactions are still forces, but I find it handy to indicate which ones are reactions and which ones forces. I'm probably going to be terrible at this, but my goal is to draw all the forces with a green arrow and all the reactions with a red arrow. I am sure I'm going to forget that at some point. In fact, I am thinking about 2 or 3 of the slides going forward in this where I have not done that. But that would be my ultimate goal kind of in all the ones we're going to create going forward. And then any dimensions to those points of reference, because if we're going to talk about moment, we need to understand how far away something is from each other or the object we're talking about. So we need all of our forces, all of our moments, and all of our dimensions that are applicable or helpful to our system. So here's a simple 2D free body diagram of a car parked. It's often helpful to have a reference point. So it looks like for this particular object, they've decided to call this point right here, 0, 0. There is the weight of the car, which we know probably is not evenly distributed, and that might have a lot of impact in some systems. But for the purposes of this, it looks like it's pretty darn close to the center. So we've summed up the entire weight and drawn it through the centroid of the car. We've shown how far away that is from what we've determined is the reference point. And we have the front wheel reaction and the rear wheel reaction. Now this is where I say we can often break a 6 degree of freedom system down to a 3 degree of freedom system. We know that this car has depth into the page, and that this reaction here for the reaction of the front wheels is really 2 wheels. So we divide it in 2 and give that to each wheel. And same here for the rear wheels. So we know that we can solve that three-dimensional problem with this 2D dimensional drawing for this application. And then we have our dimension to each wheel so that if we needed to talk about something else, we have the ability to sum all the moments about a point. Here's that same car in a slightly more complex system. It's parked on a hill now. We still have the weight acting down on it, and it's trying to go down into the center of the earth. The reactions for the car wheels are acting perpendicular. We know that the weight is actually acting in that direction there, pushing back up against the ground. But what we've done here is broken it into 2 components. The part that is the friction of the wheels to keep it from rolling down the hill, and we've broken it into this component here. So each of these we'd probably need to break down into their X and Y components, and some portion of the Y component would be due to weight, and some small component of it would be due to friction. And then in this direction, the majority of it would be due to friction, and some small amount of it would be due to weight. And then we'd be able to solve for all of these if assuming we have all the information we need here. A free body diagram of me standing on the ground and on a windy day. We came up, the reason we're still writing this book is we've done this twice this summer already, where we've come up to the cottage where we got our babysitter to look after the kids. The first time we came up, I got bit by a spider on my face and ended up in a merge. So that lost a good chunk of our week. The second time we came up, we got here 5 minutes before a tornado hit our building. So it was terrifying. And it was a spectacularly windy day. And for those of us who remember my lecture where we talk about 1 in 50-year storms that we designed for, we figure we experienced a 1 in 100-year storm. There was a lot of damage, a lot of trees down. Our neighbors had their boats destroyed. Some other buildings in line with us, they actually lost their buildings destroyed with a line of damage across the lake. They haven't said for sure it's a tornado. It certainly felt like something friggin' terrifying. It was beyond. Anyway, a diagram of me with the wind blowing on me. Let's draw the free body diagram of that. So here's me. My feet are on the ground, pushing back up. We have a reference distance between those two things. I am missing my weight arrow, so I'll add that in as well. The weight arrow for Shannon. And I'll do reaction red, forces in green. And then the wind blowing on me here, we've drawn as a UDL, or a uniformly distributed line load. We know depending on what parts of me are bigger than others, that wind might vary over the length of me. We remember from structures 1 that wind actually tends to increase as you go up further in the air, but I'm not that tall, so kind of aggregate over my height, it's probably going to be a pretty even wind distribution. So we have the length of what that is, or my height. We have the distance between my feet on the ground here. We have the reactions of my feet sticking to the ground, or what we would actually call friction. If I was wearing my hockey skates, I would probably just slide backwards in that wind. If I was standing on the ground, I'd probably stick pretty good. Maybe even my feet on ice wouldn't be enough to stop me from sliding. So we need to know what reaction is there. And then, separate from that, if we needed to, we'd look and see if the way we were resisting that was capable of resisting it. But the first thing we'd want to do is, what force does it take to keep me from sliding across the ground? And then we'd go see if the system had that capacity. Some other free body diagrams, the most common kind of beam system we look at is a pin roller. We know that the way we detail it allows this to move just a micro fraction of a littlest tiny bit, but that's enough to say that movement happened and we've got a pin roller condition. So the free body diagram of that is reaction, reaction, and the only place we can resist load going back and forth is right here, because this one is a roller. We also have the ability to resist any moment on the system or anything trying to cause this to spin in this direction. These two reactions can create a force couple to resist that moment. So if we had something trying to spin this in this direction, we know that this force would push up against it, and this one might try to pull down if it was actually trying to be lifted up out of the ground. A cantilever. A cantilever can be sideways or it can be standing up in the air. But a cantilever is only connected here at this point, so all three things that we're trying to resist have to happen in the same spot. We need something to stop it from going up and down, back and forth, and something that stops it from spinning. So for this, we would have a reaction to stop it from going up and down, a reaction from trying to stop it from sliding back and forth, and a reaction to stop it from spinning. If you guys remember, moments are a really hard thing to connect. Internally, we need to check that they have the capacity to do it, but actually making two things stick together is the really hard thing to do for moment. When you guys built your models in all of your kind of studio courses so far, if you needed a ton of glue in that spot, you were probably trying to resist a moment. Or you were trying to resist an uplift force because you had a moment applied to your system. So if you need a lot of glue, it's probably a good indication that you have a moment there. I'm just going to see. Okay. A fixed roller guide. This one's kind of interesting. It can slide back and forth here, and it can slide back and forth here. Sometimes even experienced engineers would look at this and say, that doesn't work. That's not stable. That's going to slip and slide around. Are you crazy? But let's take a look. We know this can resist a force in the up and down direction. We know it can resist a force in this direction. But look, they've drawn this funny little triangle here. This is actually a moment resistance. So it can actually resist the moment from spinning this system around. Both of these act through the same point. So we couldn't have a moment couple resisting force. So we need a moment here. This would be horrible to try to detail. I've had to do it. It's complex and difficult, so it's not a situation you want to get yourself into, but sometimes the constraints you have are the constraints you have. And if those are the conditions that you're trying to meet, there are ways we can detail it. Sometimes these are the things that get value engineered out, and the architect might lose the battle on the aesthetics they're looking for because the contractor or the owner decides it's too complex. But as long as we have all three things resisted, we can make it work and we can detail it. It just might not be the cheapest way, or it might change the looks a tiny little bit, but these things can be done. So here are two more free body diagrams of beam systems with actual forces on them. So a popular one we deal with a lot, and we did a lot of calculations with this in Structures 2, is a simply supported beam with a point load on it. So here we have a reaction at end 1, and I've just named them end 1 and 2 just so I can keep track of them when I'm documenting my forces. And reaction 2, I've indicated what units they are because I find that quite handy. We have the applied force. We have the distance between them. We have the distance of the force over on the beam. And then we have our pin roller condition because it's a simply supported beam, pin roller condition. We have our x here. When we sum the forces in our x direction on this system, there's no applied force in the x direction. So our resisting force, Rx, would equal 0. Simply supported beam with uniformly distributed load. We have a length indicated. We have an indication of what that uniformly distributed load is. So what we're saying here is, sorry, I'm wondering if I can manipulate. Oh, I probably can't now that I'm recording. I was going to try to move the size of my recording screen. We have W equals 20 kilonewtons per meter. So if you're looking at this on your slides, you can see that says 20 kilonewtons per meter. What we're saying is that every single meter of this beam has 20 kilonewtons on it. So this first meter here, 20 kilonewtons. This second meter here, 20 kilonewtons. Third meter, every one of the 6 meters here has 20 kilonewtons acting on it. And we often refer to that as kilonewtons per meter. Just basically smearing the load across and talking about it in that way. Strength, stiffness, and stability. This is a thing that even engineers kind of forget that this is the point of what we're doing. And it's kind of a handy thing to remind yourself about again and again and again. Is this system strong enough? Is this system stiff enough? And is this system stable? So stability, we're often using free body diagrams to just kind of remind ourselves if it's stable. It's a little bit harder. I say both instinctively, it's the easiest one to know. And then as we talk about things, it tends to be the easiest one to forget if you have it right or not. So every connection, every element in every system that we design has to be strong enough, stiff enough, and stable. We're going to talk about this in every single system. In fact, at the beginning of every lecture module, we're going to talk about these things. What does it take for this to be strong enough, stiff enough, and stable? And then we'll start talking about those objects or those systems that we're going to discuss in that particular module. So strength is the amount of load something can sustain prior to failure, or how much load can it take? You know, at a certain point, if I put on enough hats, they'd be so heavy that they'd squash me down into the earth, or I'd buckle, or something. So I need to be strong enough to wear all of those hats. So we'd need to keep calculating hats and see how strong my body is to resist all those hats. Stiffness is the amount of force required to make a structure deflect by some increment. Basically, we're saying as much as the system isn't moving, internally there can be movement. So the system isn't flying off into space, but the system can have internal movements. And that is when we start talking about stiffness. We often put vibration in with stiffness as well. And we're going to see, as much as we didn't spend any time talking, we like briefly talked about vibration in structures 1 and structures 2. For some of our objects, and some of our systems in this course, vibration is going to be a key component. And it's going to be important for us to know when vibration is a key component. So we're going to be talking about how much things move, how much they should be allowed to move, and what sort of vibration should we be thinking about when we're talking about these objects. And then stability, which has the worst definition in the world, is the state of being stable or the opposite of being unstable or unstable. Nonsense. Can it stand up? Not is it strong enough, but does it fly off into space in any way? Does it tip over? And so these are things that we instinctively know. My goal was to get a bunch of videos of my kids trying to make simple objects stable, and maybe going forward we might. And in fact, I'm going to get them, Dave and I will do a sample project, a very small one compared to what you guys are doing, but we're going to do a small model project, and I'm going to get the kids to do it using Lego to show you that instinctively you understand stability. Watching my kids build with Lego was really enlightening because they'll build something and it tips over. And you can see that they're frustrated by it. So they go back and they do it again. And eventually they build the thing they need to build by making it stable. If they were trying to build something that stood up and had a crank at the top, they would put a bigger piece on the bottom. And my 2-year-old now knows that if he wants to build a big thing that cantilevers over, he has to get the biggest base of Lego piece and stick it on. And what he's done there is create a moment, and he's created a footprint that has a couple at the base to resist the load that's trying to tip it over. He couldn't vocalize any of that, but he instinctively understands. We have taught them that that means it's stable, and now my 4-year-old gets really excited and goes around running, "I built it and it's stable, mommy." So if you teach them the language, they do know what they're trying to do, and they do try to understand it. So if you're trying to build something, get some Lego, test it out. Does it stand up? Get some popsicle sticks. Do you need a bunch of glue? Well, then it's probably a moment connection. I find that's a really helpful way to kind of think about it. Basically, make your free body diagram with small objects. And so these things are the things we check for every connection, every element, in every system. And those who took my course know that was a question on every exam. It was on several assignments, and it's just a thing that I wanted to drill into your head. Every connection, every element, every system needs to be strong enough, stiff enough, and stable. Structures 1 and structures 2, we spent a lot of time talking about strength. We're going to touch on it here, but that is definitely the part that the engineer would do the calculations on. And you should draw something that's in the realm of reasonable. Stiff enough is a thing where an architect might have some input. Not that you would calculate it or quantify it, but you need to understand where the thought process is coming from on it, what the criteria are for it. So surprisingly, we won't spend a lot of time talking about strength in this course. We will spend a lot of time talking about stiffness, both serviceability and vibration, and stability. So just a reminder on forces that you're going to see me talk in kind of nomenclature a lot. I'm going to add the symbols to this page. So there's a few slides that I'm going to update, and you guys might see that there's a slight difference between what's in this video and what you guys ultimately have. You'll see the download, you'll see the upload time, so you'll always know kind of what's the most recent upload. But axial forces are any of the ones that kind of happen in line with the object. So compression is the axial force that's trying to squash something, and tension is the axial force that's trying to stretch something out. Shear is talking about two planes trying to slip relative to each other. You can see that the drawing here has those two things pulled apart. It's still just this plane trying to slip past each other, the next plane, and the next plane, and these are a micro distance apart from each other, and the aggregate of all of those things trying to slip past each other gives us this kind of elongated form here where it's turned our square into a triangle. That starts to be the way the movement happens in a system. If you guys remember that concrete cracks along a diagonal kind of going up through the system, you can see that what we've taken with that square is that this distance here has tried to stretch out, and this distance here has tried to compress. So we've basically kind of changed the plane a little bit, and we're getting tension across here and compression across here. The reason that's interesting in the concrete one, you guys remember that concrete is kick-ass in compression, but crap in tension. And look, you can see this act of shearing here is causing tension along that line, which is why we would get cracks going along that direction right there. Bending. Bending is the act of trying to rotate something. The best way to think about it, again, is it's making one side go into compression and one side go into tension. So if you're bending something in that direction, the top is going into compression and the bottom is going into tension. You could bend it in the other direction and the top would be in tension and the bottom would be in compression. Torsion. We didn't spend a lot of time talking about it in Structures 1 and Structures 2. We won't talk about it that much in this as well, but every now and then it might be something we need to think about and say, oh, this thing is going to have torque on it. We're going to need to think about that and resist it in some way. But torque is kind of this combination of moment and shear. You can see we've got moment acting on it. We've got these curved arrows trying to twist the object. But look at this plane here on this side and this side. We've got this compression happening here and this tension across these sides here. So it's conceptually it's this combination of shear and moment, although not exactly, but it's a good way to kind of think about the failure modes of it. So strength design in Canada is not factor of safety, but it used to be the way we did design back in the day. And what we said was, if we have a table and Shannon climbs up on top of that table, there's the weight of the table and the weight of Shannon, and we make sure that that table is strong enough to carry its own self-weight and Shannon's weight. The problem there, though, is Shannon goes out and has a cheeseburger and beer for lunch and comes back and gets on that table, and it had been perfectly designed for its weight and Shannon, and now Shannon with a cheesy beer burger lunch has failed the table, and the table collapses. We don't want that. We don't want people going out and having a big lunch and coming back and failing the objects they need to use. So we say, all right, let's give it a factor of safety. What we used to do is say, all right, we don't know kind of how much Shannon's going to eat. Remember, this is a table designed specifically for Shannon, not anyone. This is a table for its self-weight and Shannon. That's what we're worried about here. But we don't know how much Shannon's going to go eat. So we'll give it a factor of safety. Often back in the day, we would use a factor safety of 3 to 5, for example. And so let's say this table, we design it for a factor of safety of 4. Well, what we're saying is we need this table to, you can't see the table, we need this table to be strong enough to resist 4 Shannons, but we're going to tell the world it's strong enough to resist 1 Shannon. So that the proper use is 1 Shannon, but we know that we have a built-in buffer that Shannon could go out and eat all kinds of cheeseburgers and beers and come back and not fail that table. Now, the problem is, what if Shannon goes out and eats a turkey dinner? What if the table is a slightly different thickness than we thought? This didn't treat all load types fairly. And in the end, what we do is we break it down. Okay, well, we're designing this for 1 Shannon. Well, Shannon can have some variation. She can put on some weight. Maybe yesterday she went and had a cheeseburger. And maybe what we'll do is we'll design it for Shannon with a buffer and all kinds of cheesy burgers and beers, and put a factor on that. And then we'll say, okay, but the weight of the table could have some slight differences, but we're buying that from a mill, and so we'll factor that as well. So we got away from this factor of safety design and said, okay, let's assume that every load we put on this system, we build a buffer in and we make it bigger. And then for the capacity of the table itself, we say, all right, we're pretty sure we know exactly how that material is built and we're really happy with it, but let's assume it's weaker than we think it is. Let's assume that table isn't quite as strong as we thought. And so we reduce the capacity of the table. And then we say the reduced capacity still has to be greater than that factored load. So we factor the load and we reduce the capacity. So this is the same way. This is just a different way of saying the same thing. Often we'll write it with symbols. So this alpha symbol here means a factor has been applied to the load. If you see this symbol here, we've reduced the capacity of the load. So often for different materials, you'll be provided with the factor using this symbol to tell you how much you need to reduce the capacity. And then because we don't know if we've started here in our problem or down here with our problem, we use symbols to let anybody know where the problem stands. So if we see a little subscript F, it means we've applied our factors to the loads. If we see a little subscript R, it means the capacity has been reduced. So at least we're all talking the same language. If you come to me with your loads, I'll know that you've already factored the loads and I don't now need to factor them. You can imagine if at every stage we factored the loads, we'd end up really over-designing things. This system is called limit states design. Sometimes we'll call it ultimate limit states design or ultimate limit state design. We word it a few different ways. Ultimate state is not the same thing. That limit in it is very important. So ultimate limit states or limit states design or limit state design is the system we use to design in Canada and most of the world now. The last holdout was soils, so the actual how the loads transfer into the ground. When I started, it still used the factor of safety method. And in 2010, the building code adopted the factor of safety method, or they got rid of the factor of safety method and went to limit states design the way all the other materials had. So what loads are we thinking about when we're designing these buildings? Dead loads are the self-weight and the permanent loads that we put on something. So in a building, the dead loads would be the flooring finishes. So self-weight would, if we're talking about structure, because it depends on what we're talking about. When we're talking about structure, the self-weight might be the weight of the steel beam or the wood beam. A superimposed dead load is still a permanent load, but that would be the flooring tiles. Once it's there, it's not changing much. There's not a lot of variability within that. So that's important to know when we're giving it the factor or the factor of safety or the load factor that we need to put on it. Live loads are highly variable. If everyone in the building goes out and has a cheeseburger and comes back, that can have a big impact on the load. Snow is highly variable just in the fact that it's hard to predict. We use statistics to predict the snow loads, and over the past few years that has been increasing. In Ontario, specifically Toronto, in the past it had been overestimated for years, and they slowly whittled it down just in time for climate change to really start to have an impact on the snow loads we're seeing in the area, which has increased the snow loads again in the past couple code iterations. Wind load is variable. Earthquake is a rare load case. We treat it a little bit different from everything else, and we really do rank it based on where you're likely to have an earthquake and how bad it's supposed to be. Toronto is probably the easiest place, one of the easiest places in the world to design for an earthquake. We have the likelihood of a damaging earthquake here is so low. Yes, I know we've had earthquakes here. I've been in a tall building when one hit, and it is not a comfortable feeling, but it is unlikely to cause much damage in Toronto. Montreal, different story. Ottawa, much different story. Vancouver, too. Surprisingly, northern Quebec is the worst seismic zone in Canada, not Vancouver. It's just that there's very little kind of infrastructure and people there that we don't talk about it quite as much. But when we do projects up there, it is a big part of the design. And in fact, retrofitting old buildings there is a huge, huge undertaking that the government has been dealing with for 15, 20 years. Then we have some other things that aren't as common, but might have an impact on the things we're going to be talking about in the next 9 lectures. Temperature, which can cause things to shrink, moisture, settlement, any of a combination of those things. Lateral soil loads, that's trying to, if you dig a big hole in the ground and stand beside it, that soil wants to kind of push into that hole. Well, if you dig a basement for a building and you've got soil out here, it wants to try to fill in that hole. So we need something to resist those soil loads. And one thing that we didn't talk about at all in the core graduate course was pre-stress. And there is definitely some courses, the lectures that we're going to talk about pre-stress. So that means before we've done anything, we ourselves imply a load into that system to help us remediate other things. You can imagine if you had a column that somebody wanted to squash and were worried about buckling, and they're going to push down with 1 kilonewton, but we know steel does a really good job in tension. What if we pulled on that with 2 kilonewtons? So we've got 2 kilonewtons trying to put it in tension. applying 1 kilonewton of compression means at most we'd still have 1 kilonewton of tension. So we can manipulate a system to apply a tension force that is greater than any compression forces we would ever see applied to the system, and we pre-stress it for that. And that is the concept of lightweight fabric structures, and often what we call tensile structures, is because we always want everything to be in tension, because we build them with light cables, and a cable, if you've ever had an elastic band, cannot take compression. So that's the system that we do with those. We often illustrate these in kilonewtons. Remember, 1 kilonewton is about 225 pounds, or kPa. kPa is pressure, and what we're saying, we put the units for those is, kPa is another way of writing kilonewton per meter squared. And that's saying that we have 1 kilonewton over a 1 meter by 1 meter square zone. So 225 pounds over a 1 meter by 1 meter zone. Often what we're saying with that is we've taken that 1 kilonewton and kind of made it into a ball of Play-Doh and spread it evenly over that 1 meter by 1 meter area. That's kind of roughly how we think about it, but a person standing in that zone is a really good way to describe it. When we then combine all of these according to the building code, whether it's the NBCC, the National Building Code of Canada, or the Ontario Building Code, to make sure we have the worst combination for each type of load. Each type of load might have a different governing combination. So dead load factored up might be the worst case for one part of the things we're designing. Snow and live and dead together might be a different combination for a different type of load that we need to worry about. So we have to keep track of everything and keep checking everything as we go through the systems and take a look at them. So let's just have a quick refresher about the different materials. Again, we're not going to spend a lot of time on this because we'll refresh ourselves for each kind of module that we go through. But steel is really nice because it's strong and it's really stiff. But because it's really strong, we don't always need as much of it, and it gets this perception of not being stiff because we need so little of it. And the relationship between stiffness and strength is not linear. As you guys remember when we were looking at a uniformly distributed load on a simply supported beam, strength was often kind of governed by depth and length, but stiffness was still governed by depth and length, but to the power of 4 versus strength, which would be to the power of 2 for different elements within it. So stiffness, taking away material for stiffness has a much bigger impact than it might for strength. So sometimes we have to put material back into the system, even though it's strong enough to deal with our stiffness issue. We have really good quality control in steel. It takes a specialized workforce, so people who are trained in building and erecting these things. It's isotropic, which means it behaves the same in every single direction. If we squashed it this way versus squashed it this way versus squashed it this way, it's going to behave the exact same. So that's called being isotropic. There's a lot of lead time required for steel. That's one of the main difficulties. There's others, but it takes some time to kind of get things going on it. You have to have everything resolved before you can build construction. The properties of it. It yields at 350 MPa. Remember, yield doesn't mean permanent failure or a complete failure. Yielding means that we will undergo permanent deformation. We tend to like to keep things in the elastic zone on our stress strain curve, which means any load we apply that causes internal deformation of the system, when we take the load off, goes back to normal. Once we hit yielding, the deformation is permanent. It doesn't mean that our object has failed, but we know it's on its way to failure. So we really like using yielding to let us know when we're on that limit of something's capability. But steel also has an ultimate strength an ultimate failure stress, which is 450 MPa. E is our modulus of elasticity, or the ability to measure how stiff the material is. E for steel is 200,000 MPa, and we're going to see that is one of the highest stiffnesses that we talk about in materiality. And the reduction factor for steel is 0.9. So even though it's 350 MPa until for yielding, we'll actually only take 0.9 of that when we do our calculations. So we'll say it's actually weaker than it is when we compare it to the loads that are acting on it. Most of the time, a beam will fail in bending when we go through the calculations, but stiffness might govern it. So strength-wise, bending in it is its failure mode, but because steel is so strong and we don't need that much material, stiffness starts to be a problem. And even though it's a stiff material, stiffness isn't linear to it, so we often see that the governing thing for the design itself is stiffness. Columns tend to buckle because they're strong enough and we can make them quite slender. Again, this is a stability kind of tied to stiffness problem, that buckling starts to be the problem for columns. Unless it's a really short column, which isn't often what we do, a buckling compression combination might be what governs that design. This is more just this isn't 100% of the time, this is what kind of governs the design of these elements. Wood is organic. It grows in the forest, so we don't have a lot of quality control on it. We have to categorize it and put it into groups and clusters. There's so many different types of wood. What type of tree is it? Where did it come from? And then visually we grade it. Is this one full of knots? And it rots if it's outdoors. So there's all kinds of factors that we need to consider when we're designing with wood. I'm not going to get into that right now. We might touch on it when we look at our first module that deals with wood. It's easy to get a workforce in wood. That's a great thing about wood, is that we can you can invite some buddies over, give them a few beer, and me and the girls can build a deck over a weekend. It's fast construction. You can go out and buy the material at Home Depot and start construction for most things that are in wood. There's mass timber, which is almost a different beast. It's much more similar to steel construction in its lead time. It is not isotropic. It behaves different in every direction. The way the internal forces for squashing, and squashing are all going to be different. And if you guys remember, they often broke it into parallel to grain and perp to grain, or perpendicular to grain, to know about what you were talking about. The properties for wood, because it's organic and it's variety types of materials, there's a huge variety in its properties. The strength for bending, for example, varies from 5 to 20 MPa. Remember, steel was 350, and it didn't matter what direction it was in. Shear is 1 to 3.2. Compression is 5 to 20. Similar to bending, but they're not the same for each material or each wood type. So there is a loose correlation between them, but you might see that correlation be different depending on what type of wood we're talking about. E, which is the stiffness factor or the stiffness of the material, varies from 6,000 to 12,000 MPa. Remember, again, steel was 200,000 MPa. And the reduction factor varies depending on what we're talking about with wood. For compression and tension, it's 0.8, and for bending and shear, it's 0.9. Beams tend to fail in shear or bending for wood. Stiffness might govern, but it's usually pretty close to moment calculations for wood. Columns, again, buckle, but if they're shorter, it might be a combination of buckling and compression. Tension forces are really hard to do in wood because connections govern everything in wood. Moment connections are hard, and tension connections are hard in wood. So often if we have something in a wood system that needs a lot of tension, we might have a steel element within that part of the system. Concrete, it's a composite material where we combine, even the concrete itself, is composite, where we've got aggregate and sand and water and limestone mixed together. And then reinforced concrete, which is what we're talking about, is also a composite material where we have rebar embedded in our concrete to make it act together. Concrete is great in compression, complete crap in tension. Steel is great in tension. So we throw the steel in where we have tension in our concrete to make a really good system. We have to build it twice. The problem with concrete is we need wood formwork to kind of hold this thing in place because it's liquid, and we literally pour our building into place, and it isn't able to even hold up its own self-weight until it's cured. So we need something to hold it up while it's curing. So we have to build a wood building to hold up a concrete building. And where concrete has a lot of value is when we can reuse that wood, what we call formwork. So we build the building, take out the wood formwork, and maybe it's a condo, and we take that same wood formwork and rebuild it on the floor above, and keep going up. So the more we can reuse our formwork, the cheaper our system starts to be. So again, it's great where it's repetitive. It's really slow construction because we have to wait for it to cure. That building below has to be strong enough to hold the parts above it. So we can't build the next floors until that concrete has cured enough. Concrete's pretty good with vibration because it's so massive. It's massive enough that it can dampen a lot of our vibration loads, which we're going to see has some impact on certain things. But it's also very heavy. Its own self-weight can start to be a bit of a problem. And so that can be a limiting factor in building with concrete. Oh. Yes, it is 9 in the morning, but I am very, very, very hungover. So I need a breakfast beer. And I have no small kids. And so far we haven't had a spider bite or a tornado for this trip at the cottage. So I'm going to have a breakfast beer. Cheers. Thank you. You're the best. Did you want to come say hello to your students? He's in cottage hair mode. It's very unnerving because it's backwards from what I think it is. Say hello to everyone.
Hi, guys. Nice to meet everyone.
We'll probably trade off lectures, so you'll get your own dedicated time with them. So concrete properties, it is dependent on how we mix it and how we make it. So it can vary from 15 to 50 MPa. Normally we're building around 30 MPa. That's often what's spec'd on the drawings. It might be 25 to 35, but 30 tends to be a pretty good number for what we spec on our drawings. We assume that it has zero capacity and tension. Nothing. It has a tiny little bit, but it is so inconsequential compared to its compression that we don't account for it. That's why we use the steel. Bending, we say the same thing, mostly because when it's in bending, one side is in compression and one side is in tension. So the steel does the tension work and the top side is actually in compression. So we're really, time we need to talk about bending of the material for concrete, we're really talking about the top part or wherever it's in bending being in compression. So it's a bit of a rework there on how we talk about steel. Rebar, we use 400 MPa for the yield strength. It's a different material than our normal steel, which is 350 MPa for yielding. Rebar also has a lot, it's less controlled, so it has a slightly higher strength, but it's slightly less dependable as well, which you're going to see here with the reduction factor being 0.85 instead of only 0.9. E is related to F prime C, or the strength of concrete in compression. You don't need to worry about the equation for that, but it ranges between 14 and 41,000 MPa. Again, it's a fraction of what steel is, but we can calculate it and make use of it. Concrete, slabs, their biggest failure mode is usually shear. The catastrophic failures that tend to happen in concrete are almost always in shear, especially for slabs. It might be bending, but that is rare. And if it fails in bending, it's because we've dealt with the shear, and now we need to make sure it's strong enough in bending. But shear is usually the first primary failure mode that we look at and reinforce for, and then we look at the bending and make sure it's strong enough to resist the bending loads. Columns, again, buckling. It's all about buckling for columns. Again, tension forces are difficult in concrete, and we deal with all of that with tension. We still try not to use concrete in a tension mode if we don't have to, because then we just might as well use a steel structure. Why would we bother with the concrete if it doesn't do anything? In bending, it's half in compression, half in tension, so there's value in using the concrete because the concrete does the compression work really well, and the steel does the tension work. But if we just have an object in tension, using concrete isn't a very smart way to do it. But because of this, rebar placement in concrete is critical. Making sure it's in the right spot and that it's where it needs to be is the most important thing. It's funny because the labor force doesn't have to be kind of highly trained in rebar placement. If they don't understand the critical factor of that rebar, it's very easy to make a mistake. And I'm not saying that that's always what happens, but if the people installing it it's not always intuitive that would be such a big problem. The rebar's in there, what does it matter? Making sure it's not in the middle and down at the bottom, you wouldn't think would have that big of an impact, but if we're talking about something being in bending, having the steel in the middle is going to be less effective than being down at the bottom. So the things we're going to talk about kind of going forward for each kind of lecture module is going to be how could these things fail? What do we need to do to make these things work? And so we need to kind of define them. Does it fall into if we're talking about strength, let's start with strength. Does it fall into a category in the building code? So the building code is really good at classifying different things, but it's not all things. Mostly it's dedicated to dealing with buildings. Sometimes it talks about things within buildings, like it spends a lot of time talking about cranes. It has a whole section on handrails. So those, yes, they definitely fall in the building code, and we have context that we can refer to. If we can't find the context for it in our building code, is there another building code in the world that deals with it? For example, wind on unique structures. Our building code is very linear and deals with square boxes with wind loads on it. Sometimes they have different shaped roofs, but that's about it. The Australian wind code has beautiful diagrams of various shapes and the wind loads those shapes can see. So it is reasonable that us as structural engineers would look into a code because if there's a published code, there's been testing and reasonable professionals have thought about it and done something to establish a coded system for it. If we can't find that, is there a precedent out there that we can look at and see how that was engineered? We have to try to figure out what loads could be anticipated. Is there something that we haven't thought of? And when all of that fails, we have to do what a reasonable selection of practicing professionals would do. We have to be able to go to the building code department and say, this is what we did, and we think it is reasonable that another engineer would do the same thing. You can probably find an engineer that's going to argue with you because, let's face it, engineers like to argue. But if a wide selection of engineers would reasonably make the same decision as you, then you have a valid thing that you have done. The National Building Code of Canada and the Ontario Building Code outline live loads, wind loads, and snow loads. I don't know why I have snow capitalized there, but for whatever reason I felt it was important for buildings. It has some unique structures for snow and wind, but not that many. That's where we might go to a different code. Like I said, loads for guards are in there, and often we can extrapolate. So for art structures, for example, I could imagine somebody leaning on it or hanging off of it, and I use the same loading criteria that I would for a guard then, because that's what one person can physically induce on the system. It's not all the people trying to fail something at once like a floor would be. I've often colloquially or jokingly referred to that load as the one drunk guy factor or one drunk girl factor. Basically, you get people running around and they decide to climb a thing that they would reasonably not do on a normal day. Inevitably, they will try to decide to climb something if they can. And so we design it for a person getting into this structure and hanging off of it. Anyone who watched any of the Raptors parade stuff from last year in 2019 saw that if they fits, they sits. People were climbing absolutely everything they possibly could in downtown Toronto. And I saw some of my artwork covered in people, and I realized that I was so glad I designed it to resist that many people climbing around on the structure, even though that's not really outlined in the code. And sometimes clients get pretty pissed off saying it's not meant to be climbed, but inevitably we know that it might be climbed at some point. Some types of structures have specific standards that you can purchase. The American ASCE has a lot of standards for like playground equipment, for example. They have very specific playground equipment loads codified that can be pretty comprehensive. I have, for some things, purchased these codes, and it just says, oh yeah, use the building code loads, which was a waste of $100 for that particular code, because I literally already had the building code, and I probably would have inferred that in light of any other code, would have just used the loads from the building code. So sometimes it's a bit of a rabbit hole that way, but you can usually come up with a good context for your design loads. How do we design stability? Well, do we have a reaction location to resist all the forces and moments that are on it? And the best way to do that is to draw our free body diagram. Honestly, stability all comes down to creating that beautiful free body diagram. Stiffness. Stiffness is interesting. If you guys remember from Structures 1 and Structures 2, I talked about stiffness being more of a strongly worded suggestion. If we didn't meet the stiffness criteria and there was damages to finishes, everyone would be very unhappy. So unless there's a good reason not to follow the code outlined stiffness criteria, don't do anything else. Follow the code criteria for stiffness. But sometimes it's unreasonable. An art structure, for example, that has nothing that can damage on it and a person's going to hang on it, who cares if it moves enough or deflects enough that they're uncomfortable? They'll let go and get off. As long as that doesn't cause any permanent damage to the art piece itself, what does it matter if at that moment it moved 10 millimeters instead of only the 7 that might have been code prescribed? We don't care. There's no damage coming from that additional 3 millimeters of movement. So often our stiffness criteria is about preservation of finishes and the comfort of the people around us or the person causing that movement. If you're standing in the middle of a beam and it sags 3 inches, even though it's strong enough, you're not going to feel very comfortable. That is why so many people get uncomfortable walking across rope bridges. They're strong enough, but you do not feel comfortable walking across it. So we often design things to a higher stiffness criteria than we might for strength to ensure preservation of finishes and the comfort of the people using it. So first we'll look, is there a criteria? If there's no criteria, we'll talk, do we need a criteria? Do we need that person hanging off the art structure to feel comfortable while they're hanging there? I would argue, no, we don't need them to feel comfortable. We do need to make sure that it can't turn into another failure mode. Remember, a stiffness problem can turn into a stability problem if it is great enough. And then if we do need a criteria, we might come up with what is reasonable. And that again comes back to what would a selection of reasonable practicing engineers do in that situation. Vibration, same criteria or same outline thought process. Is there a criteria? Do we need a criteria, and what's reasonable? Buildings all have vibration criteria, but they rarely are the governing factor. There are things that we're going to talk about that vibration is the number one governing factor in design of these structures. Stairs. Stairs is almost always about vibration. And it's about vibration for a few different things. There is you walking up the stair. Then there is somebody else standing on the stair and you walking up slow at a rhythmic pace. And then there's someone else standing on the stair while you run up the stair. And what is that person's experience like? If you've ever been on a pedestrian bridge, you know that they allow quite a bit of vibration on those things. And you've probably been there when a runner has gone by and you can start to feel the bridge really resonate with that person running across. So I'm not giving you guys any homework. I just want you to kind of, as you're going around the world over the next few days, start looking at static objects around you. And just kind of run it through your head just to kind of get yourself comfortable with this idea of strength, stability, and stiffness. Think about what loads are on that object. What material does it use to resist those loads? In your own head, draw your mental free body diagram of the system. Can you imagine where all the reactions are for it? Can you imagine where all the loads are being applied to it? What do you think its connections look like? Where is it connected? How is it connected? Would you think that was a moment connection or just a pinned connection? Remember, a pin can't transfer moment, but a moment connection can obviously transfer moment. What serviceability limits, if any, might have been used in the design of that? And do we think vibration might have been a concern? Again, not a exercise at all. If you feel like it, feel free to draw a few free body diagrams. If we can, I'll make a short video in the next week, or like just an image. Maybe I'll make a PDF of some free body diagrams people have drawn. If you're stuck on one, send it in. We'll try to draw and kind of give some feedback on it. Again, this isn't a required exercise. It's just to we're going to be doing this for all of the objects that we talk about at the beginning of every lecture. So I just want you to on your own, get into the process of thinking about those things. So that was the end of lecture 1, just kind of an intro back into structures and thinking about structures. We're going to talk about some really fun things going forward. I know we're both really excited about it. And there's a few topics that we've been arguing over who gets to teach you guys. If we can, we'll have a few where we'll swing it, where we record them together. We might come up with a slightly different method for that, or I'd just make the slideshow smaller and make the screen image of us bigger, so it's a little bit easier to kind of see both of us, or move my webcam back a little bit. I think next week we're jumping into stairs, which the whole lecture, that's a big one. It's probably one of the biggest ones, because we'll need to talk about what goes into the design of stairs. And then before we can talk about fancy stairs, we should understand basic stairs. We'll touch on things in the building code just a little bit, both part 3, which is your domain, and part 4, which is my domain, the engineering components of it. And then we'll get into fancy stairs. What are some unique stairs and how did they resist those? And so what we might try to do for fancy stairs is show you the free body diagram and what they thought about while they were designing it. Where were the difficult connections? And I have a few ongoing right now that I'll ask the architects if I can share the concepts with those ones with you as well. We're going to do a whole separate lecture on guards, but often stairs and guards are tied together, and sometimes they can serve the purpose of helping each other. For example, if you have cantilevered treads off the wall, but you still need a guard there, sometimes it's worth connecting the tread and the guard together, and now you've got a stringer. That guard can turn into the beam that's working for your stairs. So sometimes there's some kind of thinking about what you're getting out of the system for designing these things, while still keeping it beautiful and aesthetic. So it was great meeting all 30 of you. Again, we're really excited to be teaching this course. I think 10 lectures that are between 2 and 3 hours each. but done in moduled sections of video should be pretty handleable. But again, handleable. But there's no kind of deadline on it. So if you want to take all 12 weeks to watch 10 lectures, we're not going to worry about that. The project is going to be, there's going to be 2 small assignments, and the assignments will be done on Quarkus. It's not a test. The format it uses is a test-based format, but you're going to have time to do it, and it's mostly just helping you remember the things we've talked about. It'll be open book. You can look at your notes, and it's just a means of you guys being able to having a place where you can submit the answers. That's an easy way to do it, especially where I can agreed to take on double the class load for this when I'm already kind of jammed up. It allows it to do the marking for me for the only the assignments, but you guys will have a full week to work on it, so you don't have to worry about like you don't have to submit it until you're done. You can kind of keep working on it. You don't have to submit it until you've decided you're done the assignment. The project is going to be a sequence of steps where you identify one of the objects we talk about. So one of these, like whether it's a stair or a canopy, or maybe it's one we're not talking about, but you'd have to then go through the process of figuring out what loads you might talk about on your own, which is fine. That's great. It could be another unique structure, kind of beyond what we did in the core course, which could have been any object at all. This one, I want you to try to think of one that is structure and architecture meeting, but it doesn't have to be a normal thing. Like an art piece is not normal at all. If you have an art piece that you've been thinking of developing, what a great way to start thinking about that. And what we're going to do is you guys are going to figure out what loads would be on it, where they're applied, what your free body diagram should be. If you want, you can resolve your free body diagram. You can calculate those reactions. It's not a requirement, but we're going to see how we do that again throughout this course. And then you're going to need to build a scale model of it where you'd be able to test out some of your ideas quite easily. And then you're actually going to load it to destruction. And we're going to see if how you predicted and what it would fail at is actually how it failed. And then you're going to write a little kind of 1-page summary of everything that happened and what you might do to improve it. You don't have to go improve it, but what you think maybe you went wrong or what you could make better, how you could improve that structure or what things you might do to improve it. So more will come on that as we go through the term. So this was great, and I can't wait to dig into stairs next week, guys. Okay, talk to you then.